In this lecture, we'll be talking about the heuristics approach. Well, before I even start up with the example, let us talk about for a few minutes about heuristics. Going through the a bit abstract definition of heuristics. It is an approach by which, from the starting state, we can reach to the goal state. Definitely, but we are not sure of whether we are going through an optimized path or not. That means an heuristic approach definitely guarantees a result, but how efficient the result is, this thing is not guaranteed. Here, we'll be presenting a small example, or in fact, an example. It's a case study, a classic case study of how the heuristics can be computed, or how we can make out a better approach for computing the heuristics for any particular class of problems. So, in front of you, you are having the 8 puzzle problem, right? The state space configuration of 8 tiles on the board are provided. Now, what you can see is it's a classic 8 puzzle problem. You are having two configurations that are provided to you here. This is the first one, this is the second one. The first one is the initial configuration, the second one is the goal configuration. In the initial one, can be any configuration. Any means, obviously, we are having how many blocks out here? There are 3, 3, 6, 3, 9. In an 8 puzzle problem, one block is always vacant or empty. So I can have any configuration comprising of 9 minus 1. That means of the 8 elements, they can be put at any position in this 8 puzzle problem. Likewise, I can be provided with a specific goal state comprising of these 8 elements. The 8 elements are from starting they are from 1 to 8, right? Now in this case, typically we are having 1 2 3 7 8 4 6 blank space and a 5. The goal state must be, this is expected. Now this is the initial state, this is the goal state. We have to move from here to here, we have to move from here to here. So we have to gradually go from this initial configuration to the goal configuration. So the solution should be what? Now it should be an optimal sequence of operators. Optimal sequence of operator means, just look at these two configurations first, forget about anything. You have to move these elements in such a way, this was a childhood game, I hope many of you will be remembering. You have to move them in such a way that they come to this configuration, that means this one from this one. Fine. So you might be thinking that the elements to be moved are either 1 2 3 7 8 4 6 and 5, right? Are we really moving the elements in the 8 puzzle maze? The answer is no. We don't move, even though practically we do move, but actual movement is not of the elements but of the blank space or the blank element that will be moving. That means here I am having a blank space here. The blank space in my goal configuration is at the center position, right? So for the blank position to reach from this position to this position is the movement of the blank position one step up. That means from here to this. That means from row number 3 to row number 2. Now you might be thinking that is it the solution that if I move the blank space from the third row to the second row, I can come to the solution? No, obviously not. I need to make much more rearrangements. So what are these rearrangements? These rearrangements are to check that what are the possible combinations that this blank move can achieve? What are the combinations that the blank move can achieve? It depends on where the blank element is there. So now in the goal state, the blank element is at the center. What are the position where the blank element can be present? The blank element can be present at any of the 9 locations, right? So if it is at the corner, what are the movements of the blank element? The movement can be, towards right, then it can be one down or one towards left. One towards right. If it is at the center, it can be towards right, towards left, towards up, towards down, right? So the conditions, now I'm coming back to the actions. The condition, the move is within the board. The directions can be left, right, up and down. Left, right, up and down. In my initial configuration that you can see here, what are the directions in which my blank element can move? It can move in 3 directions. The first one is the left, the second one is the right, the third one is the up. It doesn't have a down position because the constraint has been touched. That means it is the edge of the 8 puzzle problem, right? So we can sum up this whole slide as the movement is basically of the blank element, and the blank element in coordination with the elements that are filled, they are to be rearranged. The index position of this blank element will decide that how accurate my steps are and how efficiently I am moving towards my heuristics to reach for the goal state, right? What are the moves for the blank element? The moves are left, right, up and down. Let us see further. Now, we have known about what are the things that are given and what we are doing. Let's talk about what is the problem. The problem is that which 8 puzzle move is the best? Now here you are supposed to, as I have talked about, that this is an heuristics approach, and here you have to go through the fact that which 8 puzzle move is the best, right? Now what heuristics can decide here? This is the second thing that we have to see, right? Now which move is the best? That means worth considering first. These are the 3 things that are to be answered. Let us see how we are going to deal with it. Now the actions, here they're talking about the actions. Now what are the actions that are possible? The 3 possible moves are left, up and right. Why? Because here this is my initial state and this is my goal state. Very nice. Now why it is left, up and right? Because it can go, this blank element can go either left, right and up. That means at the position of 6, 8 and 5, right? Remember, this is my initial state and this is my goal state. Now when I am at my initial state, what are the 3 states that I can achieve? That means what are the 3 moves that I can go from this state? I can reach from this state. The three moves that I can have are the movement of the blank element towards my left, the movement of the blank element towards my right. For my left, that means at 6 position, putting the blank position at 6 is this, that means movement towards left. Putting my blank element towards right, that means at the position of 5 is this. And putting the blank element up, that means at the position of 8 is this one. So I can have a left, right and up position. Fine. You can see here that there is something written as count the correct positions, and there is a value called H. There is a value of H here for left, H here for right and H here for up. Let us see how this and you can see here that H is having a value of 6, H is having a value of 4, and H is having a value of 5. Nice. Now what are these values? H are the heuristics, right? Now I am supposed to find out which move is the best. How did I get the value of H for the movement of blank element towards left? This can be calculated very easily, right? What I can do here is I have to see what are the elements in this left move. After the left move, what are the elements that are in the right position after the left move of the blank element? How am I going to compare it? I'll be comparing this hole with this goal state. This hole with this goal state. That means this whole left move of the blank element with that of the goal state. Let us see. 1 is at the correct position, 2 is at the correct position, 3 is at the correct position, then 4 is at the correct position, 5 is at the correct position, and 6 is at the correct position. So out of the 8 elements, how many elements are in the correct position? 1, 2, 3, 4, 5, and 6. So hence the value of H is equal to 6. Similarly, in the next one, how many correct positions does the movement of the blank element towards the right side creates? 1 is at the right position. Compared with that, in this case also, the movement of the element at the position of the element 5, that means the right move of the blank element creates this whole structure, that means this whole alignment. Now I'll be comparing this whole alignment with the goal one. Here 1 is at the right position, 2 is at the right position, 3 is at the right position, 4 is at the right position. So at max there are only 4 elements that are at the right position, hence H equal to 4. Now starting with the initial state, by the movement of the blank element at the up position, that means at the position of 8, this is the configuration that I am getting. Now I'll be comparing this configuration with again the goal configuration, and I'll be checking how many elements of this are in the right position as compared to that of the goal. So 1 is at the right position, 2 is at the right position, 3 is at the right position, 4 is at the right position, 5 is at the right position. Rest all, that means 6, 7 and 8 are at wrong positions. So my H value is 5 out here. So the movement of my blank element towards the left, right and up, that means the movement of the blank element at the position of 6, movement of the blank element at the position of 8, and movement of the blank element at the position of 5 will decide this configuration, and this configuration, and they will give us the value of H equal to 6, H equal to 4, and H equal to 5. So which is the best move? Here if I ask you a question, then obviously the best move will be the left move, because this gives me a H value of 6. That means more and more elements are at the right position, that means at a better position by moving the blank element towards the left. Done. So one of the questions of my heuristics approach for this 8 puzzle problem has been answered. Let us see further. Now by applying the heuristics, the 3 different approaches that can be achieved. One of the approaches we have seen now. What are the rest 2 approaches? That means, or in a way, let us talk about all the 3 approaches. The first approach is the count the correct position of each tile compared to that of the goal state. Count the incorrect position, again the same thing, of each tile compared to that of the goal state. Count how far away each tile is from its correct position, right? So applying the heuristics, I am having 3 different approaches. The first one is, again repeating it off, count the correct position, count the incorrect position, and count how far away. So in our problems in the examinations, it may be asked like the heuristics approach, find out the 3 different heuristics approach. You'll be writing the 3 different heuristics approaches are counting the correct position, counting the incorrect position, and how far away. Here you can see a probable solution for this. The name of the approaches are there, the moves are there, the left move, the right move, the up move, right? Now the approaches names are mentioned here at one position at number one it is the counting the correct position, counting the incorrect position, and counting how far away, right? Now let us see. Counting the correct position is nothing but the value of h itself, which you have computed here. H is 6, that how many elements after having the blank elements left move is at the correct position is 6. How many elements after the blank moves right position is at the correct position, h equal to 4. How many elements correct position after the blank elements up move is h equal to 5. So left it is h, for right it is for left it is h equal to 6, for right it is h equal to 4, and for up it is h equal to 5. The 6, 4 and 5 comes up here. Count the correct position is 6, 4 and 5 just below left, right and up. Fine. Now counting the incorrect position. How am I going to count the incorrect position? Since I am having total number of elements in this whole 8 puzzle problem is 8, total number of places are 9, total number of elements are 8, because one vacant space or blank space acts as a buffer which aids in the movement of the rest of the elements. So if I am having 6 at the correct position, obviously the remaining 2 elements will be at the incorrect position. If I am having 4 at the correct position after the right movement of the blank space, then definitely 4 will be at the incorrect position. If I am having 5 at the correct position after the up movement of the blank element, then I'll be having 3 at the incorrect position. So it should be 2, 4 and 3. It is 2, 4 and 3. So count the incorrect positions value is 2, 4 and 3 for left, right and up. It is very clear out here. There's another approach which is obviously very simple and kiddish. You can simply see it out here. You can compare after the blank elements left move, that means coming up here, you can compare this with this part, right? And you can see that what are the elements that are not there in the correct position. So 7 is not there in the correct position and 8 is not there in the correct position, so it is 2. Here again 4 elements are not in the correct position, here 3 elements are not in the correct position. So you can count the elements also from the left, right and up movement here, right? And you can fill up these values, count the incorrect position as 2, 4 and 3. Now comes the third approach for applying the 3 different approaches of heuristics. The third one is counting how far away. Under how far away, how am I going to calculate it? I can calculate it by seeing this thing here. After the left move, how far away means the elements that are at the incorrect position for each left, right and up move, what are the moves that those incorrect elements has to take to reach to the correct position? This is what I have to compute. Now here, how many elements are there in the incorrect position in the left move of the blank element or the blank space? There are 2 elements that are there in the incorrect position. The 2 elements are 7 and 8. Now the goal state is here where the 7 should be. The 7's position right now is at the first column of the second row, whereas 7 should have been at the first column of the third row as compared to that of the goal state. So how many moves 7 should take to reach here? Definitely 1, that means from here to here. I am having 8 here at row 2 and column 2 in the left moves part. In the goal part, 8 must be at this position, that means column 1 and row 2 in the goal. That means 1 move for 8 and 1 move for 7, that means 1 plus 1, it is 2 moves. So how far away is 2 for the left configuration of the blank move? It is 2. Let us see for the right move. In the right move, I know that h equal to 4. That means four elements are there in the correct position and 4 are there in the incorrect position. What are the elements that are there in the correct position? The elements that are there in the correct position are 1, 2, 3 and 4. What are the elements that are there in the incorrect position? How am I calculating which are there in the incorrect position? The elements that are there in the incorrect position are 7, 8, 6 and 5, right? Let us talk about 7. 7 is one step. I'm seeing this right part here, and I'm comparing it with the goal state. 7 is one move away from its right position. 8 is also one move away from its right position. And then 5 is one move away from its right position. And 6 is one move away from its right position. So 1, 2, 3 and 4. 4 moves should be there for 7, 8, 5 and 6. 4 moves for putting these 4 elements at from its wrong position to its correct position. 4 extra moves are to be done, right? How far away? Not moves. That means how far away from their actual cell. These are not the moves, in fact. They are how far away. So how far away it is? 4 for the right configuration. Let us see for the third one. That means for my blank spaces up move. For the blank spaces up move, when it is here, I'll be comparing this with my goal state again. Now when I'll be comparing this with my goal state, I'll be getting what? What are the elements that are there in the right position? 1, 2, 3, 4 and 5 is at the right position. 7, 6 and 8 are in the wrong position. I'll be comparing the position of 7, 6 and 8 with this 7, 6 and 8. So 7 can move up to 1 to be at the how far away from its destination position. It is 1 place away. 6 is also 1 place away and 8 is 2 place away. So 1 plus 2 is 4. So count how far away for the up configuration is 4. So we can see here it is 2, 4 and 4. Each of these 3 approaches are explained below. Now theoretically you can see it here. The heuristics, the first one, that means that out of the 3 different approaches, the first approach, count the correct position of each tile, compare to that of the goal state. Higher the number, the better it is. Obviously, the higher the number of the elements that are in the correct position, the better it is. Easy to compute, fast and takes little memory. Probably the simplest possible heuristics. The second approach is incorrect position. Lower the number, the better it is. Obviously, the lesser the number of elements that will be there in the incorrect position, the better it is. The best move is where the lowest number is returned by the heuristics. In the third approach, count how far away each tile is from its correct position. So the count how far away, how many tile movements each tile is from its correct position. Sum up these counts overall for all the tiles. The best move is where the lowest number is returned by the heuristics. Obviously, these are theoretical, and these all things I have explained above with an example. Now one more thing I'd like to add here is that you can see here in our problem that has been given, my initial state is this, my goal state is this. Now in my initial state, my vacant place or the blank space is at the third row. It could have been at the second row also, at the position of 8, and 8 could have been at the position of the blank element. Then this whole structure would have changed. Here, count the correct position. In the part of the count the correct position, I would have got one more column out here, left, right, up and down. In case of count the incorrect position also, I would have got left, right, up and down. In case of count how far away also, I could have got left, right, up and down here. So one more extra column could have been added here, subject to the condition that in my initial state the blank could have been this this right, left, up and down would have been there if the blank element could have been at the second row's second position. That means it is possible only when the blank is there at second row, second column. Only under one condition I'll be getting another column as the down column. Rest all things remains the same. So thank you so very much for this lecture. We'll be meeting again. Until that time, go through this part. Thank you.